To build such a large bridge over the open sea in an area that is earthquake-prone was an unimaginable risk.
It is truly amazing how such a colossus can appear graceful and almost weightless.
Everything about the Golden Gate Bridge was sensational.
Gazing at the Golden Gate Bridge's majestic suspension cables, it's hard not to marvel at the engineering brilliance behind them. But without these cables, the bridge would face disaster. Designed by Joseph Strauss and completed in the 1930s, this iconic structure stands as a symbol of human ingenuity and perseverance. So, join us as we dive into the intricate design, uncover the secrets of its incredible strength, and explore the astonishing engineering that keeps it standing tall. The Golden Gate Bridge, one of the world's most iconic landmarks, is a marvel of engineering, designed as a suspension bridge to span the 2.7-kilometer gap between San Francisco and Marin County. But why did engineers choose this design? Well, let's break it down. A suspension bridge works by suspending a road deck from cables that are anchored at both ends and supported by towers. Imagine two towering structures at each end of the bay with a massive cable hanging between them, forming a parabolic curve. This cable supports the road deck along its entire length, preventing it from collapsing. Now, why not use a simpler beam bridge? The answer lies in the scale and location. A beam bridge would require numerous piers in the water, obstructing ship traffic and driving up costs due to the deep waters, 300 feet below the surface. Clearly, this wasn't practical. An arch bridge could allow for ship passage, but maintaining its shape would require the structure to be incredibly tall and complex, making it challenging and expensive to build. This is where Joseph Strauss, the chief engineer, made a genius choice. He opted for a suspension bridge, which elegantly addressed the challenges. However, the suspension design has its own set of issues. The immense tension in the main cables pulls inward on the towers, causing them to bend. To counteract this, the cables are anchored firmly to the ground, balancing the forces and stabilizing the structure. But there's more to the story. To optimize the design, engineers moved the towers closer together, reducing the length of the unsupported road deck. This clever adjustment decreased the tension in the cables, allowing for a thinner, more economical cable design. Today, the main cables, each more than half the height of an average human, stand as a testament to this brilliant engineering. In fact, a section of these cables is proudly displayed near the bridge, giving visitors a closer look at the sheer scale of the materials that hold this incredible structure together. If the Golden Gate Bridge had been built exactly as originally designed, it would have faced a serious problem. The key issue lies in the connections, the weakest link in any structure. Connecting steel suspenders directly to the brittle concrete deck would have caused cracks, leading to structural failure. But Joseph Strauss, the chief engineer, had a solution. Instead of directly attaching the suspenders to the concrete, Strauss connected them to a steel framework. Steel-to-steel connections are much stronger and more durable. This steel structure supported the road deck, which was designed to be 27 meters wide, accommodating both current and future traffic demands. Constructing this framework was no easy feat. The foggy and windy conditions of the site added to the challenge, but the solution was clever. Prefabricate each part of the truss off-site and transport it by ship. Workers then assembled these pieces using a derrick, securing the connections with rivets. For safety, a net was installed beneath the bridge deck, protecting workers during construction. As the bridge took shape, 250 pairs of vertical cables were used to suspend the entire road deck from the main cable. Once the steel structures were in place, The bridge was painted its iconic international orange color. Next, let's dive into the intricate details of constructing the Golden Gate Bridge's concrete road deck, perched atop its robust steel framework. Steel bars were meticulously placed, then welded to the underlying steel sections. Next, the concrete was poured and compacted using a needle vibrator, ensuring a solid foundation. It might look perfect at this stage, but there was a significant challenge yet to be addressed: thermal expansion. Both the concrete and the steel structure expand and contract with temperature changes. If the bridge had been built as a single, unbroken piece on a hot day, the expansion would have exerted enormous stress on the towers and the road deck, eventually leading to damage. To counter this, engineers devised an ingenious solution: finger expansion joints. These joints, visible on the road, allow the bridge deck to expand and contract up to 4 feet during extreme temperature fluctuations. By dividing the deck into 7 sections, engineers ensured that the bridge could adapt to the environment without compromising its integrity, a masterstroke of engineering. However, there was another wrinkle to iron out. Steel expands slightly more than concrete, which could have caused issues for the concrete deck reinforced with steel bars. This differential expansion is minimal over short distances, but over the span of the Golden Gate Bridge, it required attention. That's why tiny expansion joints were installed every 50 feet, allowing for subtle movements and preventing damage to the deck. The height of the towers posed yet another challenge. Through experimentation, it became clear that a taller tower with a high sag in the cable provides far greater strength than a shorter tower with a low sag. When heavy loads are applied, the short tower design fails due to the increased tension needed in the cables to balance the load. The taller tower, however, can withstand these forces without compromising the bridge's stability. Engineers calculated an optimal height of 746 feet for the towers, striking a balance between strength and cost. Another brilliant solution in the design of this iconic structure. Now, did you know that the construction of the Golden Gate Bridge's South Tower was an engineering challenge that tested the limits of human ingenuity? Unlike the North Tower, the South Tower faced the relentless force of the Pacific Ocean. The bedrock, known as hard strata, lay a daunting 50 feet below the seabed, sloping steeply. This meant that building a foundation for the South Tower required digging deep into the ocean floor, a task that was anything but straightforward. To tackle this, professional divers were brought in to carry out underwater blasting. They planted bombs beneath the waves, clearing away debris to expose a stable surface for the foundation. Once the blasting was done, the next step was to create a steel and wooden framework on this newly prepared surface. The divers' work was nothing short of extraordinary, ensuring that every step was carefully executed. With the framework in place, the construction team poured concrete to form fender walls. These walls were essential for holding back the ocean's powerful currents, but they came with their own set of risks. The force exerted by the water was so immense that there was a genuine danger of the fender walls collapsing inward, putting workers' lives at risk. This is where Mr. Joseph Strauss, the mastermind behind the bridge, devised a brilliant solution. He proposed building a thick, reinforced concrete slab which would act as a protective barrier. Workers could then safely operate beneath this slab, shielded from the ocean's deadly currents. They accessed their work area through a specialized shaft, drilling through the boulders and digging into the bedrock below. As the digging progressed, the entire fender wall structure gradually sank deeper into the ocean, its sharp, knife-like shape allowing it to cut through the water. Finally, they reached the rocky, hard strata. With the bedrock leveled, they constructed a sturdy steel structure and laid down the RCC, reinforced cement concrete, foundation. This foundation, now shielded by the fender walls, was ready to support the towering steel structure that would soon rise above it. With the foundation complete, it was time to construct the towering steel columns. Workers assembled the steel base plate on the foundation, and then, like a giant Lego set, they pieced together the hollow steel cells that would form the towers. Each cell was carefully planned and shaped to ensure the tower's strength and stability. Next came the laying of the main cables. Cable saddles were installed atop the towers to support the massive cables, which were far from being a single solid piece. Instead, the main cables were composed of 27,000 smaller wires, with a total length of 129,000 kilometers of steel wire used in their fabrication. Workers constructed a temporary catwalk bridge to assist in this process, beginning by laying a support wire. The smaller wires were then passed over the tower, one by one, through the cable saddle and clamped by laborers. The wires were pressed tightly together using a hydraulic press and wound together with galvanized steel wire, creating the appearance of a single, large pipe. These cables were then anchored to the bedrock with strand shoe steel plates, and suspension cables were attached to the main cables, completing the crucial structural elements of the bridge. All that remained was to construct the deck structure and lay down the concrete road, a process we already talked about above. The bridge, now fully constructed, stood as a testament to human engineering prowess. Before you go, make sure to subscribe to our channel. Thanks for watching, and we hope you enjoyed learning about the incredible engineering behind the Golden Gate Bridge.